Hi, and welcome to Dr. V's AP Chemistry webcast. In this webcast, we're discussing reversible reactions and dynamic equilibrium. This is a really important topic for AP Chemistry students. So here's what I'd like to accomplish in this webcast. I want to start by discussing reactions that go to completion, and then use that to segue into the idea of reversible reactions. And once we have the idea of reversible reactions, we can discuss and describe dynamic equilibrium. So there are reactions that go to completion. Basically, all the reactions get consumed to make products. We say that they go to completion or they go to an end. And examples of reactions that do this are reactions that form a precipitate. For example, sodium chloride reacting with silver nitrate will make soluble sodium nitrate and a precipitate of silver chloride. And that silver chloride is very insoluble, and it's really not accessible to react anymore. And so the reverse reaction isn't going to happen. All the reactants make products, and that's really the end of the story. Another example of reactions that go to completion are reactions that form a gas, and then that gas is escaping from an open container. The gas is not available to do the reverse reaction. So magnesium reacting with hydrochloric acid will make soluble magnesium chloride, and then the hydrogen gas bubbles away. It's not coming back, right? And so the forward reaction is the only one that happens, and we say it goes to an end. But a lot of reactions are reversible, and so they can be returned to their original state. A lot of physical processes, melting ice and refreezing water, right? You can go back and forth and back and forth. It's a reversible process. Recharging your batteries, right? You can run the battery and then you can recharge it if it's designed to do that. And a lot of reactions do have this ability to go in both the forward and the reverse directions. We tend to associate these with closed systems, right? If there's a gas involved, it can't escape. Everything stays together, and therefore both the reactants can make products and then the products can make reactants again. It's a reversible process. And so this idea of a reversible process is really important. And PHET has a wonderful simulation on this where we can see reactants A making products B, and then the products B making reactants A, and both reactions are occurring. It's a reversible process as it goes. All right, so we can say A making B, we can say B is making A, and we can write this as a reversible reaction. Notice that double-headed arrow. Forward and reverse reactions are occurring. It's a reversible process. So let's talk a little bit more about writing reversible processes. Now, why do I have a glass of iced tea? Well, if you think about sweet tea, right, there's sugar dissolved in it. And my father, for example, likes to have his tea with so much sugar that there's a layer of solid sugar on the bottom. And so we can have a reversible process here. We use a double-headed arrow to show that. So we have the solid sugar at the bottom of the tea going into solution, and then we have the sugar that's in solution settling down to make the solid again. We have two reactions or two processes occurring, and they're reverse of each other. So the solid sugar going into solution, and the sugar that's dissolved in solution is redepositing as solid sugar on the bottom. Both reactions are occurring at the same time in your tea, and they never stop. This is a really important idea. All right. So both the forward and the reverse reactions are occurring simultaneously. Sugar going into solution, dissolved sugar settling down as the solid again. But what we're seeing is that when this establishes an equilibrium, there's no net apparent change. The sweetness of the tea isn't changing once this has been established. So let's go back to the PHET simulation and explore it a little bit more. So we let it run, and we see the reversible reaction occurring. Both the forward and the reverse reactions continue to occur. We see the green particles A making B. We see the B particles making A. Both reactions are occurring. But if you watch the simulation and let it continue to play, what we see is that the number of A particles and the number of B particles pretty much stay around the same values as long as we let the simulation keep running. The reactions are both continuing to occur, but we're not seeing a change in the number of each type of particle. That's really the central idea behind equilibrium, which is a difficult, abstract idea. So the forward and reverse reactions can establish this equilibrium, sort of a balance point where we're not seeing any macroscopic change. The definition of equilibrium is that the rate of the forward reaction equals the rate of the reverse reaction. It's really important that you understand that and remember that. Both reactions continue to occur. So in this PHET simulation, A made B, B made A. We're seeing both reactions continuing to happen. The reactions do not stop. But there's no observable macroscopic changes that we can see. The numbers of A were pretty much constant. The numbers of B were pretty much constant. If we did a time average, they weren't changing. There weren't any macroscopic changes, but both the forward and reverse reactions continue to happen. Let's think about an analogy for dynamic equilibrium. We say it's dynamic because it never ends. The reactions continue to happen. So if we think about a soccer game, you can only have a certain number of players on the field for each team, but you can also substitute players in and out. So if one player goes onto the field, another player has to leave. The number of players on the field has to stay the same. The individual players on the field can be changing all the time. So you can think about the forward reaction being subbing in, and the reverse reaction means subbing out. But the total number of players on the field at any time is constant. But the substitutions keep happening throughout the game, especially in a youth soccer game where you would have a lot of substitutions going on. Forward, back, it never ends. And yet the number of players on the team stays the same. It's dynamic and it continues to happen. So again, the reactions continue, but at equilibrium, there aren't any macroscopic changes. We're not going to see changes in, say, the color of the solution. We're not going to see changes in concentration. So we can look at this graphically and we can see initially A and B, their concentrations dropped. Concentration of C increased over time. But at some time t, where I drew this vertical line, the concentration stopped changing. And that's when equilibrium was established. So we stopped seeing changes in the concentrations of A and B and C. And that's what's happening at equilibrium. But the reactions continue to occur. So if we come back and look at our graph some more, I want to point out that A and B are both reactants. Notice their concentrations start high and drop. And C is our product. Started at a low concentration and its concentration increased, right? And eventually they level off. Another important point and a common misconception is that the concentrations of reactants and products do not have to be equal to each other at equilibrium. In fact, in this situation, A and B and C all have different concentrations at equilibrium. What's equal at equilibrium are the rates. The rate of the forward reaction, the rate of the reverse reaction. The concentrations of A and B and C work out to be what they are. They do not have to be equal to each other. It's very important to remember that the reactions continue to occur at equilibrium, that the rate of the forward reaction equals the rate of the reverse reaction. So here's my kind of clunky hand-drawn version of that. The forward reaction rate slows down, the reverse reaction rate sped up, but they level off. It's meant to be a straight line. It was kind of hard to draw that freehand, but the rates are what are equal at equilibrium, not the concentrations. It's a very common misconception. Don't fall for it. Now, there are different situations that can lead us to dynamic equilibrium. We can have phase equilibrium between solids and liquids. We can have solution equilibrium, dissolving a solid in a solute. So the solid is the reactant and the aqueous dissolved substance, perhaps, is the product. And we can have chemical reactions that establish dynamic equilibrium as well. They're all equilibria. The forward and reverse reactions continue to occur. The rates of the forward and reverse reactions are equal, but different situations where we can describe equilibrium. Now, the last thing I wanted to mention about equilibrium was the idea of the ratio of products to reactants. We know at equilibrium, the reactions continue, but the concentration stopped changing. There's no macroscopic changes. And so we can actually talk about the ratio of product to reactant, and it's constant once that equilibrium has been established. And it's called the equilibrium constant. And we can actually write equations for it. And this is such an important idea that I'm going to do a whole separate webcast on just the idea of the equilibrium constant and how we write these expressions and what they mean. But that's too much to do in this webcast. So let's summarize what we've talked about in this webcast. Some reactions are reversible, and they can establish a dynamic equilibrium. When that has occurred, the rate of the forward reaction equals the rate of the reverse reaction. That's the definition of equilibrium. The reactions do not stop, and there are no macroscopic changes that you can observe. And that's a really, really important that my AP Chemistry students understand these ideas. If you found this webcast to be helpful, subscribe to my channel, leave a comment, and also like the video. Study chemistry every day. Really pay attention to your equilibrium concepts and skills.